Today we're going to be looking at implicit differentiation. Before now, all the differentiation we have looked at is talking about explicit differentiation. But now, today in this module, we want to look at implicit differentiation. The few lines you are seeing on the screen is quickly explaining how to apply solve implicit differentiation, just the steps to take. Now let's quickly look at this example that is staring us in the face on the screen right now. I want to find the dy dx of that implicit function or equation that we have on the screen. Is not different from the principle of differentiation we have learnt before. So we are going to differentiate each of the term we have on the screen. I'm going to differentiate 2x squared. I'll differentiate the minus 3y squared and also differentiate 5. The same principle that we applied in explicit differentiation also apply. Now if I want to differentiate 2x squared, that gives me 4x. As you can see on the screen, if I differentiate 3y raised to power 3, I'm going to have 9y squared. That shouldn't sound different from what you have learned before. Now the only difference here is that as soon as you differentiate any term that has a y, you place the y dx by its side. Place the y dx by its side. Okay, now if I differentiate the 5 on my right hand side, that gives me 0. That's the derivative of a constant, which is always 0. Now I want to make, next line, I make dy dx subject of the formula. Then first of all, I pick my 4x and take it to the right hand side, and I have minus 4x. Then dividing both sides by minus 9y squared, then I have what you have on the screen. Don't forget and take notes, anytime you differentiate an expression or a term that contains the y, you quickly place by its side the y dx. Good. That's implicit differentiation. Now let's move ahead to derivative of trigonometric functions. Derivative of trig functions. Now we know what trig is. When we have trigonometric ratios like cosine, sine, tangent, then we're talking about trigonometric functions. Now let's look at this question on the screen. Find the derivative of y equals to cos 2x. How do we solve that? Now I want you to remember what we did before. In explicit differentiation, we talk about function of a function, which is also known as chain rule. Now we are treating this question as function of a function because we have two functions there. 2x is an algebraic function, then cos itself is another function. Okay, so we are treating this question as a what? As a function of a function. So the first step is, let's quickly make our 2x u. Let u be 2x. Then if my u is equal to 2x, then my y is going to be is equal to cos u. And that's the formula for function of a function, which is chain rule that follows. Then substitute, if I differentiate du dx, then I have 2. If I differentiate, that is already substituted. If I differentiate dy du, that gives me minus sine 2x, because the derivative of cosine is minus sine. Don't forget, in one of our pages in this particular module, we talk about function of a function, or we have done it earlier. So we have it in one of the pages of our modules. That's the derivative of trigonometric functions. Don't forget, you can refer back to that particular page. Okay, now let's look at the derivative of inverse function. When we say inverse function or derivative of inverse function, all we need to do here is to obtain our dy dx, and the inverse of the dy dx is what gives us the x dy, and that is the derivative of inverse function. Okay, and that's what you are seeing on the screen. All you need to do is find dy dx, then when you do the reciprocal, that gives us the x dy, which is the derivative of inverse function. Now let's quickly look at this question to buttress our point. If y is equal to 2x raised to the power 4, we want to find the x dy. So the x dy is already talking about the derivative of inverse function. Once you don't see dy dx, the x dy is derivative of inverse function. Okay, now let's look at the solution very fast. If I do my dy dx for the question we have here, our normal differentiation principle, what do we have? 8x raised to the power 3. Then if I do the reciprocal of that, which is the x over dy, I have 1 over 8x raised to the power 3, and that gives us the answer that is staring us in the face on the screen. That's quite easy, right? Good. Let's look at the derivative of exponential functions. If I have y equals to a raised to the power x, that a is a constant. If it's a constant, say 2. So I have, say, y equals to 2 raised to the power x. My dy dx, that's an exponential function. So my dy dx is going to be y log a to base e. And don't forget, log e can be written as what? Ln. Is also the same thing with ln, which is what? Natural log. Ln is written as ln. ln. Okay, good. So if I have the other one, if y equals to e raised to power x, then my dy dx is going to be the same thing, e raised to power x. So these are the important two derivatives we need to know under derivative of exponential function. Don't forget, the first one you are seeing for y equals to a raised to power x, I can also write dy dx to be equal to y ln a. Y ln a. Good. That brings us to higher derivative, which is the last thing in our module. This particular module we are treating. Higher derivative. The 2y over the x squared is what we call the second derivative. When I differentiate a function, the result I have, if I differentiate again, is going to give me second derivative. That's the second derivative. Now, the result of my second derivative, if I differentiate that again, then that gives me the third derivative. In the same vein, if I differentiate the result of my third derivative one more time, then that gives me the fourth derivative, and it goes on and on like that. Thank you for paying attention.